For electromagnetic induction, there is a bird in the background, I know, and you're just going to have to bear with that because I can't, and I really don't want to get it to keep quiet. So, if you look at electromagnetic induction, there's a few terms that you need to know and be familiar with before we can actually look at this chapter. So we're going to start by looking at what are these things actually. So when we say B, what do we actually mean? And when we draw the symbol phi, what do we actually mean? Now B we've been using in the previous chapter, and that's always the density. It's the magnetic flux density. So it tells you which direction the magnetic field is moving, but it also shows you the strength of the magnetic field by telling you how dense these lines are. And I showed you that as well. If you draw them denser, you are already showing that the field is stronger. So B is the magnetic flux density. Now, if you remember what density means, it always tells you something per unit volume or something per area. Now, in this case, it's going because there's lines moving like that, we're going to look at the specific area. So if you look at this little diagram there, the density would mean the amount of field lines passing through that area. And I'm going to do a bit of a rough diagram for you just now, but if you could imagine this little green block moving in this area between the North and the South Pole. The number of lines, because they are evenly spread in a uniform field, the number of lines passing through that green area would not change. So the magnetic flux density between these two poles do not change because it is a uniform field. Now, so density, let me just write it. It's the number of lines per unit area. So we can almost say lines per area. But flux is the total number of lines that passes through a specific area, the total number of lines. So it doesn't have to be 1 square meter, it could be 2 square meters. So if you have 10 lines in that little block and you add another little block next to it that's still inside this magnetic field, then that means there's going to be 2 of these blocks. So you're going to say 2 times by the number of field lines there, so 2 times B. And that is why flux is then B times by the area, B times A. We'll get to the cos theta now. So if we just look at that part there, flux is the total number of lines. So it's the area that we just said, 2 if we have 2, 1 if we have 1, times by the area. Times by the magnetic flux density, how many of them are going through one block. Now I'm going to look at this one. I know it's a simple form, but I'm going to try and explain to you the difference between these two. Because in this chapter, it is important that you know the difference when there is a change in magnetic flux and when there is no change in magnetic flux. But you must also know that you mustn't say there's a change in the magnetic flux density, because often there isn't. The only way I can change the density now here is to use stronger magnets. If I use stronger magnets, these lines are going to be closer together. So then I will be changing the magnetic flux density. But if I have a fixed magnetic field, like I normally have in motors and in generators, the north and the south pole, then these lines are evenly spread. So I'm going to try and draw. I know my 3 dimensions is not going to work as nicely as what we would like it to. So I'm going to draw as soon as this allows me to. Come now. My board is just stalling for 1 second. There we go. So I'm just going to get rid of those little lines. So I'm going to try and draw that little area there. So let's say I have this little area here, and that area is now, or this block or coil or whatever it then is, going to move through this magnetic field. It's a very simple way of explaining it, but I'm hoping you will understand. Now, if I am here, is there any magnetic flux? So if you look at this coil or area here, so we're looking at this area here, there's no flux because there's no lines. The magnetic flux density here, still the magnetic flux density, that hasn't changed. So now when I move this, so I'm going to move it all the way through. So let's just see step by step. When I move it from here to here, now it goes from 0 lines passing through this area to 2 lines passing through that area. So was there a change in magnetic flux? And this is the question that you have to keep on asking yourself in this section. Is there a change? The triangle means change, remember, in the magnetic flux. And from there to there, yes, it was 0 and then it was 2. So yes, there is a change in magnetic flux. Now I'm going to move it more. So from there to there, how many lines is passing through the area now? 1, 2, 3. So still, while it was moving in, it went from 0 to 2 to 3. So yes, there's still a change in magnetic flux. But now while it is moving, I'm moving my field instead of my coil. While I move this coil inside my magnetic field, so 1, 2, 3 lines still, so it changed from 3 to 3. So was there a change in magnetic flux? It didn't really change. It went from 3 to 3, so it's still the same, no change. Again, there once I move there, 1, 2, 3 lines. Only when I start moving out of my coil, now it went from 3 to 2 lines. So is there now a change in magnetic flux? Yes, I can say yes, and this is important for later. So there's a change in magnetic flux as I move. So when I moved in, it was increasing, and when I moved out, it was decreasing. So both times there was a change in magnetic flux. But if you look at the magnetic flux density between the North Pole and the South Pole, that still remained the same. Now, in this chapter, we're often going to look at things turning in a magnetic field. So if you look at something turning in a magnetic field, again, we need to look at the number of field lines passing through this area. So I'm first going to just do it in the logical manner, and then we're going to look at the equations that you have. Let's move these out of the way. So if you look at this one here, when it's in this position, so my North Pole, South Pole, still here, you can see the magnetic field lines are the purple lines going from north to south. So now if my coil is in this position, or whatever it is, coil, loop, solenoid, armature, any of those words can be used. So if it's in this position, you can see there are all these lines passing through the area. So that means I've got a high magnetic flux. When it's in this position, if you look at this area, the yellow area there again, there's nothing. No lines are passing through that area. So my magnetic flux here is 0. Let me just put it in here. So here I have a magnetic flux that is a maximum. And here I have a magnetic flux that is 0. Again, look at my B. Did my B change? Magnetic flux density here and magnetic flux density here should be exactly the same if it's the same magnets. Anywhere in between, I'll have an angle, and that is why you will see that you have that cos theta in your equation. So the cos theta is because any angle between the maximum and the 0 will give us between 90 degrees or 180 degrees. I'll go through the angles now. Will give us a magnetic flux somewhere between the maximum and the 0. And you'll see this nicely when we look at the graphs at the end. So now, if I don't just have one little loop, I just have to mention that quickly. If I now go and put another loop and another loop on top of this one, the loops, the symbol that we use for extra windings, so extra windings in our coil or extra number of turns is just an N. So if I now go and add an N to this equation, then we're not going to say magnetic flux anymore. Then we're going to say magnetic flux linkage. But it's exactly the same as magnetic flux. The unit is the same. It just means for every loop, there is now another bunch of lines that's cutting that area. So you can just remember the wording. Also, remember there's no real calculations in this topic. You're going to have to use these equations to explain things rather than calculate. So magnetic flux linkage is just N times by phi as it is in the definition here. Magnetic flux linkage is just the number of turns times by the flux. The units I have, because we don't really calculate, we don't talk about the units that often, but it would be nice if you know them. The units for magnetic flux density You will see those in questions often. Magnetic flux density is Tesla. It's a capital T, Tesla. The magnetic flux, for the magnetic flux, it's just Weber, big W, small b. And magnetic flux linkage, because it's just multiplied by the number of windings, is also Weber. Now, if we look at the maths here quickly, the angle, that cos theta, sometimes confuse people, but the cos theta is the angle between the normal of the area and the magnetic field. So if you have an area like here, I'm just going to use that one. This is my area. The normal is always a line that is drawn 90 degrees to the area. Now the angle between the normal to the area and my magnetic field there is 90. So if you think mathematically about this, cos 90 is going to give you 0. So BA cos theta is going to be 0 because BA cos 90. If you look at this one here, you're going to have cos. Now look at the angle. The angle is between the normal to the area and the magnetic field. Now this time it's 0 or 180, and if you get cos of 0 or 180 degrees, you know that that is 1. So that means it's the maximum it can ever be. So between 0 and 1, if it's any, or if my angle is between 180 and 90 or 90 and 0, the value is going to be a fraction. So it's going to, of cos theta. So that means anything else will give you a value between the maximum and 0. So yeah, the math you can work out for yourself. So these equations are given to you on your information sheet, the BA cos theta, and the F is BIL sine theta that we did earlier. They're all there. And if you want to look at this YouTube video, it also explains this quite nicely. But now we need to move on. We need to go and see, when is there a change in magnetic flux? So I'm going to move on. Now, just moving these out of the way, what you're going to see in this chapter, in the previous chapter, there was an electric current that was switched on and motion was the product, was the result. So it was electrical energy into mechanical energy. Now this time we are actually physically going to move a wire. Now there's lots of videos on Khan Academy. They go into a lot of detail, but I know there are some of you that like knowing the finer details because it helps you understand the simpler things. So if you look at a wire moving now in a magnetic field, so we are physically moving it. Don't take the lines there too seriously. This wire is now moving in the magnetic field. But what that means is that that little electron there, that little electron there, and that little electron there are physically moving. So remember that electron is a charged particle. So if a charge moves in a magnetic field, it's going to experience a force. So a charge moving in the magnetic field, however it moves, this time we are physically moving it. We apply a force on the electron and make it move. So I'm going to just write over these. We are going to move the wire in this direction. But now what's going to happen is this little electron here is going to experience a force. And we call that force an electromotive force. And you've seen this before. The EMF is also called a potential difference or voltage. Now, if there's a potential difference, positive, negative potential difference, then that electron will move. So the electron will start to move, and if I have an electron moving, I have a current. So this is the principle on which the electromagnetic induction works. I have a moving electron motion, so I have a charge moving in a magnetic field. That charge then, because it's moving in a magnetic field, will experience an EMF, and this is where you need to start focusing because this is how you will explain it. The EMF that is there due to the change in magnetic flux will then cause a current to flow. Now we need to look at the directions. You can again use so this is the movement of an electron. Please remember that we are using conventional current and not electrons. and therefore it is going to be a little bit different. The diagram just explains it quite nicely. Now, and it is from the Khan Academy video that you can go and watch. Now, if I look at this wire, so that means I am moving the wire physically in this direction. Again, you can use your slap rule, or that I call the slap rule, the right-hand vector rule, and you can say, I'm going to slap from north to south. So take your palm and face it. Now remember, the slap rule always use the right hand, which means you never have to change hands. So you face your palm from north to south. Your fingers will go in the direction of the green because the input this time is the force or the movement, and it makes you think about the energy conversion. So you're taking your fingers in the direction of the green. Please do it while I'm talking through it. So point your fingers in the direction of the green line. You are slapping from north to south, and then you need to, that will give you, your thumb as your output, and that will give you the direction of the current from positive to negative. So you will see that the magnetic field is going this way, and therefore the electron, or the current, the conventional current, is going to be in this direction. You could have used your left-hand rule as well, but remember, for generators, we use a right hand. For the Faraday's law, you're still going to use FBI. B is from north to south. Your thumb is still F, so that's going to be the first green line I drew to the right. And then your middle finger will give you the current, which is the exact same thing there. So you could use either one of the rules. I'm not going to spend too much time on it because you've practiced it before. So you could have used this or this, and you will see that you'll get the directions as I've shown it there. Now, just quickly saying it again, what's important here is that you need to know that when I'm moving the wire, so that means there has to be a change in the magnetic flux. If there is a change in magnetic flux, there will be an EMF induced. The EMF induced will cause a current to flow. Now, this brings us to Faraday's law of electromagnetic induction, which is super important. Because what his law says, so many diagrams. So I'm just going to move one out of the way. Actually, I'm just going to go back to the previous page because here we have it all. Sorry, you can now stand up quickly and stretch your legs and wake up again and make sure you're listening to me. There. Faraday's law then basically says what we've just said. It says there will be an EMF induced if there is a change in the magnetic flux. These are not equal to each other, but they are directly proportional to each other. And now you can think as well, if I'm going to move this faster, then the electrons moving through the field lines faster. So almost you can say they're going to be pushed more. So now what's going to happen is the EMF therefore will be greater. So if I make it faster, remember the time is getting smaller. So I can do the change in time at the bottom of the line. And this is Faraday's law of electromagnetic induction. The EMF induced is directly proportional to the rate. You know this by now in physics. Whenever there's a delta T at the bottom of the line, it's rate. The rate of, and then you look what's at the top of the line, change in magnetic flux. You can stop there, but you can say magnetic flux linkage. So we can add an N there because remember there's not always just one loop. There's sometimes more than one winding. And this is Faraday's law. EMF is directly proportional to the rate of change in magnetic flux or magnetic flux linkage. Now, how can I get this EMF to be bigger? And again, the equation helps you. We already said one. If I make the time that is underneath the line smaller, which means I'm moving it faster, I will increase my EMF because they're inversely proportional to each other. If I add more windings, I will increase my EMF because they are directly proportional to each other. If I increase the change in my magnetic flux, now remember also magnetic flux is equal to B times by A. So if I increase any of these two things, the strength of the magnets or the area, then I will increase the EMF that I'm going to induce. So please use the equations to determine the factors that affect the induced EMF. You have your equation, you can see the windings immediately. You can see that you want the time smaller immediately. And then if you remember that, and this is also on your information sheet, that flux is B times A, then using stronger magnets will also increase the EMF. Now, we also need to look at Lenz's law, because if you look at the equations, you will see that it's not just Faraday's law that's important. There's another part to this equation. So this gives us Faraday's law, but it also gives us Lenz's law. And how does it give us Lenz's law? Just by that negative that is added into the equation to make it an equal sign. Let me just move this away quickly. This I actually just put in to show you that it doesn't always have to be, you can move the coil, you can put the magnet, move the magnet, and I actually, when I did this in class, had the FET simulation open, so I would definitely say, go to the FET simulation and play around with it, because it could be two coils moving relative to each other that you'll see in the past paper question. It could be a magnet moving into a coil, a magnet moving out of a coil, but you all did that in class, I'm sure, so I'm not going to spend too much time on that. That is just all the different ways in which you can create a change in the magnetic flux. Because remember, if you do not have a change in the magnetic flux, you cannot have an EMF induced and you cannot get a current to flow. So that is why these diagrams were here. Now, if you look at the minus, and I maybe need to use this one here to show you this. The negative is because Lenz's law, if you read it, it says the induced current. Now remember, the induced current is because of the induced voltage. It's not the original, there isn't an original current, so it's the current that you are making. Flows in a direction as to set up a magnetic field. So that means you are making a new magnetic field. It's not an existing magnetic field to oppose the change in magnetic flux. Now, again, I'm sure you've done this in detail in class, but I'm going to go through it again because it sometimes causes a bit of confusion. If you now look at this little magnet here, I'm wondering if I made it separate. No, I didn't. So if you look at this little magnet here, if I'm moving it into the coil, sorry, I thought I did have a separate one somewhere. It doesn't matter. So if I'm moving this magnet into the coil, it means the change that now you will see again, if you look at the law, it says set up a magnetic field to oppose the change in magnetic flux. So now what am I doing? I'm pushing a north pole into the coil, simply said. So how can I oppose that? How can I repel that magnet? And now you need to think for yourself, if I want to push away that north pole, I'm going to set up a magnetic field. I'm going to make a new magnetic field. So this coil is going to form a magnetic field to oppose the entering magnet. So to oppose that, I need to form a north pole on this side and a south pole on this side. So what's happening now is I am creating this by inducing an EMF that is causing a current to be created. So it will only happen while the magnet is moving. If the magnet is just chilling there and standing still, nothing is going to happen. So the magnet has to be moving into the coil or out of the coil for a new magnetic field to be set up. So now if there's a north pole there, now you can take your right hand again. And remember, if you use your right hand, your fingers must go, your thumb must point towards the north. And if your thumb points towards the north, you will see that the current is going to flow over the top, underneath to the bottom. So that's going to be the direction of my current. If you were looking from this side, and that is how the questions is sometimes asked, that's an I. If you are looking from this side, then if you look at the current and you look into your hand, basically as it is that coil there. Now this is 3 dimensions again, so please work with me. Your thumb is pointing towards your face, and that means the current is going to be anti-clockwise. Just going to do quickly for if it's moving out. So if we take that same magnet and we're now moving it out of the coil, so we're moving it in this direction, I'm moving a north pole away. So again, how can I oppose the change in magnetic flux? To oppose the change in the magnetic flux, I need to pull this magnet back because I am moving it away. So that's what I'm doing. So to oppose that, I need to pull it back. So how can I pull a north pole back? By creating a south pole on this side, which means there will be a north pole on that side. Again, if you point your thumb to the north pole and you look from the right hand side as we did before, you will see that now the current is flowing clockwise. So by pushing the magnet in and out of the coil, I will create a negative, positive voltage, positive voltage. And the same with the current, because in the same coil, remember the voltage and the current will be directly proportional to each other, only in the same coil. So that's the Lenz's law as well as Faraday's law. Now, quickly for a generator, we're going to do a different video for transformers because otherwise this one is getting way too long. So for a generator, basically what you need to know now is the same as what we've just done and the same as in motors. The only thing now, you're not going to see a power source. So there's not going to be an AC source or a DC source. An AC source would be shown like this. That would show AC. A DC source, you normally have a battery, or they'll have a power pack there with a plus and a minus. Now, what happens here, for this cycle that you are seeing here, you can see this is the motion. So this must be physically moved around. And again, this is a very nice YouTube animation that you can go and watch. So while it's and the colors actually change in this one, so please go watch it. So while this is moving up, it is inducing a current in a specific direction. But while it is moving down, it is inducing a current in a different direction. So if you look at the blue wire only, the blue wire here is moving up, so the current is flowing upwards in that direction. If it moves downwards here, the current is going to be going downwards in this direction. So you are actually going to create an alternating current because while it's moving up, current flows from positive to negative. While it's moving down, current goes from negative to positive. So that is why we are calling a generator like this, and all generators will always give us alternating current as an output. We're going to look at how to rectify this when we look at the transformers video, but alternating current is always what is produced by a generator, except if you go and rectify it. So you will not see a commutator here because that will already rectify it. You will see 2 slip rings. Now, why do we have the slip rings there if we're not wanting to change the current? Alternating current is perfect. Although it goes on and off, it doesn't matter. The slip rings now are just there to connect your whatever you have here. This could be a light bulb, and the light bulb would shine like it is here. It could be a voltmeter to give you your induced EMF. It could be an ammeter to show you the current, but it's not going to be a power source. That you need to know. So the current is going to go positive, negative, positive 0, negative 0. Okay, remember there's a 0 because you'll see this one actually flickers, but it goes so fast that your brain can't really pick it up. If you take a slow motion video on your phone, that's quite nice because then you can see it flickering. Now, for this one moving, we always have AC, but the slip ring here, there's a brush and it just slides over that ring. And there's a brush and it just slides over that ring that's connecting your armature or your coil or your solenoid, whatever you want to call it, to the outside circuit without these wires getting tangled. So that's all the slip rings are there for. So they do not change the current. It will still be AC that comes out of the generator, but it just means that the wires don't get tangled by connecting it to the outside circuit here. So there we go. That is Faraday's law. And we've spoken about how we can increase the EMF. So in the next video, we'll look at the last little bit of this chapter.